Welcome to The Explainer. Today, we are diving deep into one of the most powerful and elegant algorithms in machine learning, the support vector machine, or SVM for short. We're going to break down how it finds the absolute best dividing line in a sea of possibilities, and then we'll get into the clever mathematical trick that lets it solve problems that, at first glance, look totally impossible.
I mean, just take a look at this. How would you even begin to draw a single straight line to separate the blue dots from the red ones? It looks impossible, right? But by the end of this explainer, you're going to understand the brilliant mathematical transformation that lets an SVM solve this kind of puzzle with surprising ease.
Okay, so here's our game plan. We're going to start with a fundamental building block, the hyperplane. Then we'll see how an SVM finds the best possible boundary. After that, we'll talk about dealing with messy, real-world data using soft margins. And finally, we'll unpack the kernel trick, which is really where SVMs get their superpowers.
All right, first things first. Before we can build the whole machine, we have to understand the most basic part, the hyperplane. So in a simple two-dimensional space, like what you're seeing here classifying emails, a hyperplane is, well, it's just a straight line. That's it. It's a boundary that we draw to separate our data into two different groups.
And this idea scales up beautifully. When we add a third dimension, our hyperplane is no longer a line. It's a flat plane. And this is the key concept. A hyperplane is just a decision boundary, and it can exist in any number of dimensions you can imagine.
Now I know, equations can look a little intimidating, but this one is pretty straightforward. It's the universal address for any hyperplane. The x's are just your data's features, and the w's are weights that the model learns. Basically, you plug a data point into this equation. If you get a positive number, it's on one side of the line. If you get a negative number, it's on the other. Simple as that.
So a hyperplane splits our data. Great. But just finding any line isn't good enough. Not even close. The whole goal here is to find the single best one.
Just look at this. There are tons of possible lines that could separate the spam from the ham, right? I mean, you could draw an infinite number of them. So the big question is, how does a machine learning model decide which one is the absolute best choice?
And the answer to that is the core idea of the SVM. It's called the maximal margin classifier. The idea isn't just to separate the classes, but to do it with the widest possible street or margin between them. The best line is the one that gives the most breathing room to the closest points from each group.
Now, this idea of a perfect wide margin is fantastic in theory, but let's be real. Real-world data is almost never that clean and tidy.
And that's why we need to move from a rigid maximal margin classifier to a more flexible, soft margin one. See, the strict version is a perfectionist. A single outlier can mess it up completely. The soft margin approach is way more practical. It aims for a good balance by being okay with a few mistakes here and there. So how do we control this flexibility? Well, we introduce something called a slack variable, usually shown by the Greek letter epsilon. Every single data point gets one of these, and it's basically a little measurement of how much that point is breaking the rules. What's really cool is how this slack variable gives us a status report for every single point. If epsilon is 0, the point is behaving perfectly. It's on the right side and outside the margin. If it's between 0 and 1, the point is still on the right team, but it's stepping into that street or margin. And if epsilon is greater than 1, well, that point has gone all the way to the wrong side of the line. It's misclassified.
So this is the ideal situation. Epsilon is 0 for every point. They are all perfectly classified and sitting comfortably outside that margin. This is exactly what we'd hope for in a clean data set.
But these two images show the messier scenarios that soft margins were built to handle. On the left, you see points that are inside the margin, they're violating it, but they're still on the correct side of the line. On the right, you see points that have completely crossed over. They're misclassified, and the slack variable tells us just how wrong they are.
Okay, so we can't just let these errors run wild. We need a way to control the total amount of slack we're willing to put up with. And that's where this hyperparameter C comes in. You can think of C as a tuning dial for the model's tolerance for mistakes. Or even better, think of it as setting a budget for how many errors the model's allowed to make.
And now we get to the most powerful and frankly the coolest part of support vector machines. This is how we're going to solve that impossible problem we saw at the very beginning.
Look at the data on the left again. A straight line is never, ever going to separate those points. But what if we could pass that data through some kind of black box that transforms it,
reorganizes it into a new space where it is easily separable.
Well, that black box has a name. It's the Kernel Trick. And it's an absolutely brilliant, computationally efficient shortcut. It lets us get all the benefits of working with our data in a much higher dimensional space, but without ever having to do the incredibly heavy math of actually transforming and calculating those new coordinates. It's a total game changer.
Now, this trick is amazing, but it's not a one-size-fits-all kind of deal. Using it effectively means you have to choose the right kind of kernel for your specific problem. There are 3 really popular types of kernels, and each one is capable of creating a different shape of decision boundary. The linear kernel is just our basic hyperplane, perfect for data that's already pretty easy to separate. The polynomial kernel can create curved boundaries, and the radial basis function, or RBF kernel, is the most flexible. It can create all sorts of complex shapes, even circles, for really tricky data. For the more advanced kernels like RBF, there's another tuning dial, usually called sigma or gamma. Think of this as a flexibility knob. As you turn it up, you can see here it allows the boundary to get more complex and fit the data more tightly. And that brings us to the biggest question of all. How much complexity is too much? The power of SVMs comes from these parameters, these tuning dials like C and gamma. But with great power comes the very real risk of overfitting. That's when your model gets so good at memorizing your training data that it fails miserably on new data it's never seen before. The real art of machine learning is finding that perfect balance between fitting your data well and building a model that can actually make useful predictions in the real world. That balance is everything.